space complete. Why is this? So let us see why this is the case. Again, why is this the case? So there could be, what are the possibilities, right? So one is that there is no quantifiers, but TQBF means all the variables are quantified, which means if there are no quantifiers, there could be no variables. So this means it's a formula without any variables. So formula of only constants. So if it's a constant formula, it is something like the Boolean, like true or true and false, something like that. Right? Just take a 3 plus 4 or 3 plus 4 multiplied by 6, some numerical equation without variables. It's just like a Boolean equation without variables, and one can easily evaluate that without much difficulty. So this is certainly in P space. What if there are quantifiers? Let us look at the cases. So look at the first quantifier. There are two possibilities. The first quantifier is an existential quantifier, there exists, or an universal quantifier for all, right? So let us consider both. So let us say the first quantifier is there exists quantifier, existential quantifier. So it says there exists x1 and something else, right? Something else. So there could be other variables in this something else. Now, how do we solve this? So we want to check whether, so now the formula is saying, so some formula, right? This formula is saying, so this could be psi of x1, x2, something, right? Where the psi also contains quantifiers, or maybe let me just say phi of this, right? Where phi also contains quantifiers. It will have quantifiers because, so now we could set x1 to true and see whether phi is true, because everything else is quantified inside phi except x1. So if you set x1 to be true, phi becomes a TQBF instance, and you could recursively do the same algorithm. If you make x1 to be false, again phi becomes a TQBF instance, because the only variable that is not quantified in phi is x1. X1 is set to false, and the rest are quantified. So again, it's a TQBF instance, and we want to check whether so the question is, does there exist in x1 such that phi is true? So you will check either is phi x1, is phi true, x2, x3, etc. Is that true, or phi? So phi true, x2, etc. Is this true, or phi false, x2, etc. is one of these true, because both of them are TQBF instances. Now when the first, so again it's a recursive thing. The second thing is when the first quantifier is a universal quantifier. Again, it's not very difficult. You could think of it as for all x1 something, but it's exactly what I described for the universal existential quantifier, except that now we want both cases to be true. So we will check both branches and check if both of them are true. So what needs to be done here? It is a recursive call. So at each instance, the tentative assignment of phi is x1 is stored, and then in the next level of recursion x2 will be stored, and the next level of recursion, the next assignment of x3 will be stored, and so on. So if there are m variables, right, m variables in this fully quantified Boolean formula, we need to remember order m variables assignment, so that is order m bits are required, and then finally at the end we will just make we will just try to evaluate whether this is true or not, right? So we will just have an equation of constants, a Boolean equation of constants, which can be evaluated, and then at the end all these branches have to be combined. Like existential means there should, any one of the choices should be true. So all this can be done at the base, at the top level, right? So the space usage is order m, because there are m items to be remembered at most, right? So again, this is the high level idea, and this proof is there in Sipser. Read full proof in CIPSR. Anyway, I explained the full proof here. Maybe I just didn't write it down, but it is there in CIPSR anyway, right? So this is the proof that TQBF is in P space. So the space usage is order M, which is linear space, and this space is for all the recursion levels, not just one level, because at each level, like constant amount of space is required to store whether x1 is true or that kind of thing, true or false. Now let's come to the bigger question, which is whether it is P space hard, just like NP hard. We want to show that all the languages in P space are reducible to TQBF. For all A in P space, A should be reducible to TQBF, right? So it might help to recall some details of the Cook-Levin theorem proof. Okay. So if A is in P space, then this is going to be similar to that, but just that we wouldn't go to the details because we have already seen the details in the Cook-Levin theorem. So we'll just appeal to what we did then. Okay. Okay, if A is in P space, there is a P space machine that decides A, right? There's a P space deterministic machine, right? Now, given a string W, right, we can construct a formula such that W is in A if and only if that formula is in TQBF. That is a high level idea of the proof, right? This is how you do reductions, right? You want to show that given a string W is in A if and only if some fully quantified Boolean formula is in TQBF, right? This is what we want to show. So how do we try to show this? Okay, this is the goal of the reduction. The second point of the reduction is that the construction of the instance phi should be in polynomial space, polynomial time, right? Because this is a polynomial time reduction. So the construction of this formula should be in polynomial time. Okay, so how is that going to work? So as I already said, there is a P space machine M that decides A. So W is in A if and only if M accepts W, right? So we will use M and W to construct this formula, right? Okay. So if M accepts W, that means there's a computation table that you can draw, right? We know it's a polynomial space machine. Let us say the space, let's say it has single tape. Let us say the tape usage is n power k. Okay, the tape usage is n power k. And what is the number of what is the height of this computation table? It is a maximum number of rows it can have. Each row corresponds to a configuration of the machine. How many configurations can we have before we start? If we see the same configuration again, it means we are looping, right? Which means we have come to the same configuration again. Again, we will come back to the same thing and we are looping. So what is the maximum number of distinct configurations that you can see? And we've done this calculation many times. It is the maximum number of configurations that we can have for a space bounded machine. So if we have an n power k space bounded machine, the number of configurations will be 2 power d n times n power k, where d is some constant, right? And n is the length of the input. So this is like Cook-Levin theorem, but in Cook-Levin theorem it was time bounded. So the number of rows was n power k, and because the time was n power k, we said that the columns also will be n power k, the space usage will be n power k. But here it works differently, because here we first know that the bound on the number of columns or the space usage, and because of the columns are bounded, the space is bounded, we know the bound of the configurations, hence the time of the computation will also be bounded. It will be exponential in the space. Again, we have seen this d time or d space fn is contained in d time 2 power order fn, right? So it's the same thing here. Now again, this is a deterministic machine, right? So just like in Cook-Levin theorem, we can write a formula, Boolean formula, to check whether Ci or Ci plus 1 is a proper successor of Ci. Sorry. A configuration I plus 1 is a successor of configuration I. This is, we can write a Boolean formula for it. And this formula will be of size n power k. So given to check whether some configuration C is a, or maybe I'll just make it more clear here, Ci plus 1 is a valid configuration of Ci. So basically we need to check, we know the start configuration, right? Given a particular input, it's known. We know the accepting configuration. Again, we can do some things to make it, we can force the machine to have a unique accepting configuration. And we need to know whether there is a path from the start, or path meaning a sequence of configuration from the start to the accepting. And we know that the maximum number of steps that we can have is 2 power d n power k steps. So can this table have a valid sequence of configurations such that the first is a starting configuration, last is the accepting configuration, and every configuration is a valid successor of the previous configuration. Right? Again, this is exactly what we did in Cook-Levin theorem proof, just that in this case we are bothered about, just that in this case one is that we have a deterministic machine, so presumably the number of successors are less. But that doesn't really feature in the computation anywhere. 2, the number of rows are higher. Right? There we have n power k rows. Here we have 2 power d times n power k rows, which is exponential in that. Okay. Now let us write a formula for this. So let phi c1 c2 t. So what we will do is we will end up writing a fully quantified Boolean formula for this. So we will use all the quantifications and that we want. So the goal is to come up with something. Generally we want to say, does there exist a sequence of configurations that takes you from C1 to C2 in t steps, right? So now if we can accomplish this, then we can set C1 to C start, C2 to C accept, and T to 2 power d times n power k, right? So then we can solve whatever we want. Okay, so let us see what is C1, C2, 1. Can we move from C1 to C2 in one step at most? Right? C1, C2, 1. So what do you mean by one step at most? Either the C1 and C2 are the same, which means 0 steps, or C1 and 1 step computation gives you C2. Right? So either C1 equal to C2 or C1 to C2 in one step. And this is not that difficult to do because C1 equality can be easily checked. And C1 to C2 in one step, again, it can be checked by what we saw in the proof of Cook-Levin theorem. We had this phi move, which was essentially this, making windows into tables and so on. So both of this can be done, so that is fine. So this formula is of size, I think, n power k. Or order n power k, this entire thing. So that is good. Okay. Now we want to see whether we can generalize this for not one step but t steps. So let us see, again we saw Savage's theorem. Let us see how to write this in t steps, because if you write in t steps, like if we do it like in Cook-Levin theorem, we will have to write C1, C2 is a successor of C1, C3 is a successor of C2, C4 is a successor of C3 and so on, which will mean an exponential set sequence of such things. So which is 2 power d times n power k times n power k, which will be right. So we cannot afford to do this, to check phi C1 C2 1 and phi C2 C3 1 and C3 C4 1 and so on, because this will be exponential size, so we cannot afford to do that, right? So we cannot do that. So how do we do this more intelligently? We want to reduce the size of this formula. So what we will try to do is something that we tried in Savage's theorem already. We will use recursion. So if there is a weight from C1 to C2 in t steps, then there should be a middle point at t by 2 steps, t over 2 steps. Where were you? Let us say you were in some intermediate configuration called M1, right? So we don't even know what M1 is, but there may be some configuration called M1. So I could write, does there exist an M1, right, such that from C1 to M1 you can go in t by 2 steps, and M1 to C2 you can go in t over 2 steps, right? C1 to M1 in t over 2 and M1 to C2 in t over 2, right? So basically this is the midpoint of the table, right? So C1 here, M1 here, which is roughly at the midpoint, sorry, small m1, and C2 here. So if you can go from C1 to C2 in at most t steps, then this should be possible, right? Right. So now let's see what can be done. So now we could possibly repeat this trick again, right? So there exists M1 such that this is true. Now I could possibly rewrite this part C1 M1 t over 2 in a similar fashion by this red color stuff, and M1 C2 t by 2 into this blue colored notation. So this here and this here. Basically between C1 and M1 there has to be an intermediate M2, and between M1 and C2 there has to be an intermediate M3, right? So we are checking whether C1 to M2 can be traversed in t by 4, M2 to M1 can be traversed in t by 4, M1 to M3 t by 4, and M3 to C2 t by 4. That gives you this kind of formula. But notice what is happening here. I have split the original C1 C2 t into 4 parts, C1 M2, M2 M1, M3 M1 M3 and so on, and the t became t divided by 4, and it is, so now the t became 1/4 and we have 4 parts, but now this is expanding and expanding, and now this doesn't seem to be, and I think even if we try to unroll this t by 4 into single steps, this will be actually the original situation again. We will have an exponential sized formula without any size reduction. So this is not going to help, right? This is just some I'm just using recursion but not really making progress here. So the length is not decreasing here. So now, so this is whatever we had in Savage's theorem does not really help, but we now use a new trick called folding. So what does folding mean? We'll see now. So consider the top formula again. There exists M1 such that phi is C1 M1 t by 2 and phi M1 C by 2 t by 2, C1 t2 phi M1 C2 t by 2. Now I am going to write this in a new way. So instead of writing phi C1 M1 t divided by 2 and phi M1 C2 t divided by 2, I will just write it as, so there exists M1 here, there exists M1, same thing. I will write it as C1 M1 and M1 C2 are the two pairs, right? So I will define new two variables, C3 and C4. Whenever C3 C4 are equal to C1 M1 and M1 C2, right? I will check phi C3 C4 t by 2. Whenever C3 C4 are C1 M1 and M1 C2, I will check phi C3 C4 t by 2. So when C3 C4 is C1 M1, I am checking phi C1 M1 t by 2, which is what we have the first term here. And C3 C4 is M1 C2, I am checking phi M1 C2 t by 2, right? So for all C3 and C4 such that they are like this, they are in C1 M1 or M1 C2, I do this, okay? So I am using there exists in M1 and for all C3 C4 in this set, right? So now I am using some new kind of expressions here, right? So I am using contains is a member of C1M1. How do we write that in a Boolean setting? It's not very difficult. So what you do is you can have a this particular part, this blue underlined part can be rewritten by this part. Sorry, can be rewritten by this entire thing. So whenever C3 C4 is equal to C1 M1 or C3 C4 is equal to M1 C2, right? So this is M1 C2. This kind of looks like an E, but it is C2. When this happens, this implies that phi C3 C4 T2 T divided by 2 must be true. Okay, so the rest is same. Phi M1 for all C3 C4. Whenever C3 C4 is equal to C1 M1 or C3 C4 is M1 C2, phi C3 C4 T by 2. So now the first part is now the only thing that is remaining is the equal to symbol and the implies symbol. Now finally, I leave it to you to think how to write the equal to symbol and the implies A implies B and A equal to B. How do you write it in a using just Boolean formulas? These are very, very simple exercises. Maybe you might have seen this in the first class in Boolean logic, so you can think about it. This is not very difficult. So you can the point I want to impress upon you is that all this can be done in using Boolean formulas. So now the formula is something like this. Okay. So this entire formula is now some constant multiplied by n power k. Okay, the part after the quantifiers. Okay. Now again, phi C3 C4 T by 2 is something that we need to go deeper into. So phi, how do we go deeper into that? Again, we will use exactly the same thing. I can define intermediate states C5 and C6 and the intermediate state M2 and then variable C5 and C6 such that maybe I'll just write it a bit C5 C6 is equal to C3 M2 or C5 C6 is equal to M2 is equal to M2 C4. And if when that happens, this implies phi C5 C6 T divided by 4. Okay, so this is how you expand out this quantity, the blue underlined quantity, phi C3 C4 T divided by 2. So now when I combine all this, so recall we were trying to write a formula for phi C1 C2 T, which we first wrote it as phi there exists M1 such that for all C3 C4 something, and the rest. So I can write it as there exists M1 such that for all C3 C4 there exists M2 such that there for all C5 C6. There will be some formulas involving C3 C4 C1 M1 all this, and C5 C6 C3 all this, and then finally we will have phi C5 C6 T by 4 as part of this, which again we go deeper and deeper into. So the point is that each level adds only a linear some constant multiplied by n power k, right? Which is this is what I have written here in the part that I am underlying now. Each level needs extra space is some constant times order. So order size of C means order size of a configuration space, right? And we know the size of a configuration is order n power k, so it is still another constant, so it's still order n power k. This is the extent of memory required at each level, right? And at each level, notice that the t became t by 2 and then t by 4, right? So every level the t is halving, and we know what to do at the base case when t equal to 1, right? This is what we could do. This is what we did, right? So the base case is at 1. So how many levels are required to go from t to t divided by 2 to t divided by 4? So it is log t number of levels. So or the number so the height of the so I'm saying log h here, where h is the height of the computational table, which is 2 power d times n power k. So log h is the height of the computational table, so where maybe I'll write that also. H is equal to height of computational table, which is equal to 2 power d times n power k. So when you take log of that, it is just d times n power k. So this is the number of levels, and at each level you require order n power k space. So the total space used is some constant times d power k, sorry, n power k multiplied by order n power k, which is order n power 2k with a constant. So it is order n power 2k. And this is the total space required to write down the formula. So this means that this is the total space required to for the computation of the formula, and even to write down the formula, it's a similar amount of space, right? So this is a recursion length, and this is the number of space required, right? So hence and the correctness is kind of evident, right? Because again, from our experience in the Cook-Levin theorem, this formula captures whether there is a sequence of configuration that lead a string to be accepted, which happens when the string is accepted by a machine, which happens when the string is in the language, right? So again, everything is if and only if. So the correctness of the reduction is evident. The time complexity is total space is n power 2k, and the time taken for the computations also, this is a very structured thing, that's also is polynomial time. So that's so just to summarize this, we defined what is p space, which is polynomial, it's in space analog of p. We defined p space completeness, again, which is a space analog of kind of a space analog of np completeness. And the first p space complete language that we saw was TQBF, which is short for true fully quantified Boolean formula, where all the n variables are quantified. We saw that SAT, QSAT2, tautology, everything is in TQBF, everything is a sub problem of TQBF. And we saw why TQBF is p space complete. The fact that TQBF in p space is rather straightforward, and the proof that any p space language can be reduced to TQBF requires us to go through computational table and some simplifications in the Boolean formula that encodes the configuration. And that is about it for this lecture. I'll complete the rest of the p space completeness in the next lecture. I just wanted to add one more thing. So notice that we are doing this under p space polynomial time reductions, and we saw that SAT is contained in TQBF. Tautology can be represented as a TQBF instance. QSAT2, QSAT k complement, all of them can be represented as a TQBF instance. This means that SAT is an NP complete language. All of NP is contained in p space. All of co-NP, tautology is a co-NP complete language, is contained in p space. All of sigma 2 is contained in p space. Sigma k is contained in p space. Pi k is contained in p space. So the entire polynomial hierarchy is contained in p space. This is what it means, right? So think about this particular fact. So all of NP, co-NP, sigma 2, sigma k, pi k, all are contained in p space. And with that thought, I think I will close this lecture. And in the next lecture, we will see a couple of more instances of p space complete languages. Okay, thank you.